Hi, everyone. My name's David. I'm one of the academic mentors for CHEM 1301A this year. And today I just want to talk about some stuff from the atomic theory section of your course, just to get you guys ready for your midterm. Okay, so the first thing I want to talk about is light. So light's a type of electromagnetic wave, and it is necessary to talk about some of the properties of these waves, right? So generally, we describe these electromagnetic waves, or EM for short, um, in terms of their frequency, their amplitude, and their wavelength. So the wavelength is the distance between two identical points on the wave, or two cycles. The frequency is the number of cycles per second, and the amplitude is the maximum displacement in the vertical direction. So basically just up and down. And we also have a relationship for between frequency and wavelength, and that's given by V is equal to C over lambda, where V is your frequency, lambda is your wavelength, and C is your speed of light, which is approximately 3 times 10 to the 8 meters per second. So it makes sense that if you have a higher frequency, you have a lower wavelength and vice versa. And just taking a look at the electromagnetic spectrum there, specifically in the visible region, which is between 400 and 750 nanometers, we know that wavelength increases from left to right, while energy decreases from left to right. And you guys should roughly know the regions corresponding to different types of radiation outside of the visible region. So just in relation to each other, so you have gamma rays, X-rays, UV, and then on the other side of the visible region, you have IR and radio waves and all of that. But really the most important one is the visible region. Also, you should know that I guess light intensity is given by the square of the amplitude. And if you have a higher amplitude, you'll have more intense light or a brighter light. And conversely, if you have a lower amplitude, your light will be dimmer or less intense. Moving on, I want to talk to you guys about the Bohr model and the emission spectra for the hydrogen atom. As you all should know, electrons can be promoted to an excited higher energy state and then relax back to a lower energy state, releasing energy in the form of photons, which are just packets of light. And I'm sure many of you are familiar with the equation E is equal to hv, which gives the energy of a photon, and that follows directly from the Rydberg equation. A really core concept in chemistry as a whole is that energy or electron energies are quantized. So they take on specific values, 1, 2, 3, and there's no in between. I can talk more about that in the next slide, but in terms of the Bohr model, you guys should be familiar with the different emission lines for the hydrogen atom. So the Lyman series, the Balmer series, the Paschen series, etc. You guys should also be familiar with some of the limitations of the Bohr model. So for example, it didn't explain why the n equals 1 electrons wouldn't just get pulled towards the nucleus. It didn't account for any of the fine structure that you see in the hydrogen emission spectra. And by that, I mean where you would expect to just see one line, you would actually see two lines spaced really close together, and that's just because of spin-orbit interactions. And it's also only valid for one electron systems, so not super applicable. Okay, so moving on to the quantum mechanical model. I hope we're all familiar with the double slit experiment and how that showed the wave-particle duality of light. Simply put, wave-particle duality is the reason why energy levels are quantized. It's actually not that simple, but that doesn't really matter. You should also know that you can get both the wave function and the energy corresponding to an electron by solving the Schrodinger equation. You guys don't really need to know the specifics of the Schrodinger equation, but it can be useful to understand. So the Schrodinger equation is a second order partial differential equation, which you guys don't really need to know. But basically, when you solve the equation, you have these things called boundary conditions that you use, which make it so that you're only allowed to have certain solutions. So that's kind of where the quantization aspect of it comes from. If you're at all familiar with linear algebra, it's an eigenvalue problem. If you're not, you can think of an eigenvalue as kind of a scaling factor. So in this case, our E is our scaling factor. It's just that E can only take on very specific values. But again, all that stuff is more or less beyond the scope of this course. It's just somewhat useful for understanding some of the concepts. But back to the more important stuff. What's a wave function? Wave functions describe orbitals, and the square of the wave function describes the probability of finding the electron in the XYZ domain, or at some point in the XYZ domain. You guys should also be familiar with constructive and destructive interference. So if two waves are in phase, you'll have constructive interference. If they're out of phase, you'll have destructive, and they'll cancel each other out. You guys should also be familiar with how to find the number of nodes for an orbital, which is just n minus 1, or the principal quantum number minus 1. When you square something, you make the entire function positive, and you can't really have a negative probability. So here are just some pictures of the shapes of the atomic orbitals and their corresponding quantum numbers beside them. Okay, so now I want to talk about electron configuration. So when you're answering electron configuration questions, you always have to keep the Aufbau principle in mind, which just states that electrons fill orbitals in order of increasing energy. And the other way around, when you ionize atoms, electrons are taken from the highest energy orbital available. And let's just quickly remember that generally you fill the 4s before you fill the 3d, but when you ionize d block elements or transition metals, you'll take from the 4s orbitals first before you take from the 3d. Okay, so the last thing I want to talk about are orbital diagrams. These basically show you how electrons are distributed within a given sublevel. And when you're drawing these diagrams out, you always want to keep the Aufbau principle and Hund's rule in mind. So let's remember, you fill orbitals from the lowest energy orbital to the highest energy orbital, and within the same level, let's say the 2p level, you fill each orbital with one electron until every orbital in that level has one electron, such that they're all in parallel spin. After that, you can then start doubling up within the same orbital, and two electrons in the same orbital must have opposite spins. But there are some exceptions to those two rules, as I'm sure you guys remember from high school. You have your typical copper and chromium examples, and they're exceptions because you get half shell stability and full shell stability, so it's just energetically more favorable. And I guess the next thing I want to talk about would be the allowed wave functions for an orbital. And when you're answering questions on your exam about wave functions corresponding to a given orbital, really all you want to be doing is look at the quantum numbers. So your n, your L, and your m. So the principal quantum number you get from your electron configuration. Your L comes from the type of orbital that you're working with, and your m will come from your L value. Really, it'll be either plus L or minus L. So that's how you get to the answer.
Hi, my name is Reina. I'm also an academic mentor for CHEM 1301, and I will go over 2 practice problems for Chapter 2.1. So for the first question, it is asking you to identify between which orbits the transition is for a violet line in the emission spectrum. First, you need to identify that emission of visible light is known as the Balmer series, which is characterized by a transition from n greater than or equals to 3 to n equals 2. So here, we cross out D and E. Next, according to the electromagnetic spectrum, violet has the shortest wavelength, and therefore the highest energy in the visible light region. So we choose C, orbit 6 to orbit 2, which would result in the highest energy released out of all the options. Now question 2. Which of the following wave functions best denotes the last filled orbital of tellurium? First, we need to find tellurium on the periodic table, which is in row 5 and group 6. So now we can write out the electron configuration for tellurium, which is krypton, 4d10, 5s2, 5p4. The last filled orbital must be one of the three orbitals of 5p. So we can write out the quantum numbers for 5p as follows. N equals 5, L equals 1 for a p orbital, and M equals -1, 0, and +1. So for a wave function psi and Lm, the only possible option out of these would be A psi 511.
My name's Heather, and I'm going to be covering the periodic trends. So before we look into the 4 periodic trends, it's important to understand effective nuclear charge, as it's the basis and really helps explain the other periodic trends. So the effective nuclear charge is the net charge felt by the valence electrons of an atom. So this must be a positive charge, as the nucleus is positively charged, but it also takes into account the shielding from the core electrons. So the higher the effective nuclear charge, the stronger the attraction between the valence electrons and the atom's nucleus. So going across a period from left to right, we know that the nuclear charge increases since the atomic number or the number of protons within the nucleus increases, and we know that the number of core electrons remains constant within this rower period. This means that the effective nuclear charge must increase. So with a more positive nucleus and the same shielding from the core electrons, the valence electrons will experience more of a pull to the nucleus. This is also known as a net positive charge. We can also see that the effective nuclear charge increases going up as there are fewer core electrons to shield the valence electrons. The first trend we're going to cover is atomic radius. So atomic radius is defined as half the length of a bond formed between two atoms of the same element, which is really just describing the size. So the trend here is the atomic radius increases going down the periodic table and moving from right to left. So we saw on the last slide that the effective nuclear charge increases going from left to right, meaning that the attraction between the valence electrons and the core the nucleus increases, pulling in everything tighter and making the atom overall smaller. Then, as we go down, the number of core electrons increases as another orbital is present, so the space they occupy must also increase. There are a few exceptions of this due to poor shielding in the D and F orbitals. For example, gallium is smaller than aluminum, even though it's further down in the periodic table. So the next trend is ionization energy, which is a measure of the minimum energy required to remove an electron from the valence shell when the atom is in its gas phase. So the trend here follows the same as effective nuclear charge, where it increases from left to right across the periodic table and increases moving up the periodic table. So we know ionization must always be a positive value, and each successive ionization energy increases as the remaining valence electrons will share the same pull by the nucleus as before, but it is now felt by one less electron, meaning that they're held tighter each time an electron is removed. And again, there are some exceptions to this, such as boron having a smaller first ionization energy than beryllium, and oxygen is easier to ionize over nitrogen. The next trend is electron affinity, which is the change in enthalpy, delta H, or energy, when an atom in its gas phase gains an electron. We again also have first electron affinity, second electron affinity, just by adding in additional electrons. So in this photo, we're showing the first electron affinity, but we can add in a second electron to produce the second electron affinity. The overall trend follows the same as the effective nuclear charge, where it increases left to right across a period and increases going up. Electron affinity increasing means the change in enthalpy becomes more negative after the addition of electron. Electron affinity can be both thermodynamically favorable or unfavorable depending on the atom and how many electrons are being added. And just a reminder that negative enthalpy or negative delta H is favorable. So the final trend is electronegativity, which is basically the pull of electron density an atom has in a chemical bond over another atom. So this follows the same trend as the effective nuclear charge increasing from left to right and upwards, as smaller atoms have a stronger attraction or pull of electrons to larger atoms, with fluorine being the most electronegative atom. Here's just a practice problem regarding the periodic trends. You can go ahead and pause the video and work through it yourself before I explain the answer and how I would approach the problem. So the first thing I would do here is I would go through the question and pick out the key terms. So which is correct ranking the species of increasing ionization energy? So I think the last three terms here are really the most important. We know that increasing is meaning from smallest to largest, and then we have to go back and remember either the definition or the trend with ionization energy. I find it easier to remember the definition and then reason out what the trend would be, just because there's so many terms you guys are going to go through this semester. It's easier than trying to memorize all of them and keep them all straight. So we know that ionization energy is a measure of the minimum energy required to remove an electron from the valence shell of an atom. We also know that the effective nuclear charge is going to increase from left to right as well as upwards. So we can reason out that it will require more energy to remove an electron when this electron is more strongly pulled to the nucleus. So this lets us figure out that ionization energy will also increase from left to right and going up. So from here, I would just go through all of your options and see if they follow an increasing ionization energy trend. So firstly, we're going to look at hydrogen, lithium, and sodium. So hydrogen, lithium, and sodium, and we can see that they're going against the trend of increasing ionization energy. In other words, they are decreasing, so we can go ahead and cross out A as an option. Option B, we're going to look at iodine, bromine, and chlorine. We can see that they are increasing in ionization energy, as it's going to be harder to pull an electron from chlorine than bromine or iodine, since that electron is more strongly pulled to the nucleus. So I wouldn't go ahead and circle this as our correct answer because we haven't gone through all the options yet, but I'll just put an arrow and that will remind us to come back to it. Option C here is looking at oxygen, sulfur, and selenium. So here we can see oxygen, sulfur, and selenium. Again, these are going downwards, same as we saw in A. So these are decreasing ionization energy. So we can go ahead and cross out C as an option as well. And finally, D, we're looking at hydrogen, beryllium, and aluminum. And these three follow the complete opposite trend, or sorry, these three do not follow the trend of increasing ionization energy, as they do increase going from left to right. However, they are also going down the periodic table. So they are not an increasing ionization energy. So then we can go back and we know that B is the only option that we had originally. So we can circle B and say it is the correct answer.
Hey guys, my name is Kylie, and this section is going to focus on chemical bonding and some of the topics related to it. So these are things like Lewis structures, formal charges, and resonance. And so I'm going to be doing some of those, and then Bradley is your other academic mentor, and he's going to be doing the other sections. Okay, so to start off, we're going to talk about the different types of chemical bonds. And so just a note for this slide, anytime you see the abbreviation EN, That stands for electronegativity. So that's just a little helpful tip as we go through things. Okay, so out of all the chemical bonds that make up compounds, it can be divided into two major categories. So we have ionic and covalent. And then you can see here that covalent can get further subdivided into two more categories, which we'll talk about later. So we'll start with ionic bonds, which are formed between elements that have a large difference in electronegativity. So if you want a number value for that, it would be like a difference of greater than 1.9. But usually in your questions, you won't be given the actual numbers. And it's just kind of helpful to know that it's going to be a bond between an atom with low electronegativity and an atom with high electronegativity. So then it might also be helpful to know some examples of those types of atoms. So our low electronegativity atoms are typically like your metals in group 1 and 2. So that's on the left side of the periodic table. And then your high electronegativity atoms are things like oxygen or your halogens, so chlorine, fluorine, things on the right side of the periodic table. Another key thing to know about ionic bonds are that they involve a complete transfer of electrons. And so you can see in my example here, which is NaCl, so there is a ionic bond between these. And so the one electron that's usually around sodium has been transferred to chlorine. So now chlorine has 8 electrons around it instead of its usual 7. And then I also included this picture here because it's good for visualization purposes, just to understand that compounds that have ionic bonds form this type of lattice structure, and so it's very rigid and strong structure. Okay, so now moving on to covalent bonds. The key differences from ionic are that we have smaller differences in electronegativity, and also instead of a transfer of electrons, we have a sharing of electrons between the two atoms. Now, the details on this sharing is what gives us our two subcategories, which are polar covalent bonds and non-polar covalent bonds. So with polar bonds, we have an uneven sharing of electrons between the two atoms. And with nonpolar bonds, we have an even sharing of electrons. So basically, the electrons are perfectly evenly distributed between the two atoms. And so you can see that in this picture here. It's kind of, this is a nonpolar covalent bond, and so that's why the color is kind of even all the way throughout. Whereas you can see in this polar covalent bond, we have electrons being more concentrated towards one side. And so again, this sharing idea comes down to the electronegativity of the two atoms. So remember, overall with covalent, our differences in electronegativity are already not as big as with ionic bonds. However, if there's still kind of like a difference, like an intermediate difference, then that's where we get our polar covalent bond. And then if we have a very, very small difference or even no difference at all, which would be the case if we have a bond between two of the same atom, because then they have the same electronegativity, that's when we get the nonpolar bond. And so just a note is that you can see that I included the actual numbers for the difference in electronegativity for all three categories. But like I said before, your questions won't usually ask you about specific numbers, and it's more important just to be able to identify like what the electronegativities of the two atoms are, and then what, like how big the difference will be between them. Okay, so now moving on to a practice problem. Part A says, which one of the following has the most polar covalent bond? So looking back here, we want polar covalent bonds. So the two categories that we're trying to eliminate are ionic bonds and nonpolar covalent bonds. And so immediately I can eliminate B and C. And that's because I can see that they're ionic. So looking at B, which is NaCl, we can see that we have an atom on the left side of the periodic table and then one on the far right. So that's going to lead to a big difference in electronegativity. And we have the same thing with RBF. So we have one atom all the way down here on the left and one all the way over here on the right. So these big differences in electronegativity we know are going to give us ionic bonds. And so I'm just going to write down there that these are ionic. And then we also know that we can eliminate D and E because these are a bond between two of the same atoms. So they're going to have no difference in electronegativity at all. And that's going to give us a nonpolar covalent bond. So then that leads us to saying that our answer for question A is answer A. And just to kind of verify that that makes sense, our bond would be between C and O. So we can see that those aren't two of the same atoms, so there will be a little bit of a difference in electronegativity. So it's not going to be nonpolar, but they're still close enough to each other on the periodic table that it's not going to be a huge difference that makes it ionic. So it makes sense that that would be a polar covalent bond. Okay, and then for part B, it says, which one of the following has the highest melting point? So anytime you see a question that's asking about high melting point, immediately you want to think ionic compounds. And the reason for that is if you go back to this picture of the lattice that I put, remember I said that that's a very strong compound. So it's, or a very strong structure, sorry. So it's going to take a lot of energy to break that apart to become a liquid or to melt it. So if we're thinking about ionic compounds, then we know that we're basically going to be focusing on B and C. So we can eliminate those other options. And then when deciding between B and C, now is when we want to use our periodic trend in atomic radius. So R, B, and F are going to be quite different in size because we can see that one is all the way down here in row 5, whereas F is up here, it's going to be a lot smaller. In comparison, Na and Cl are very similar in size because they're both in row 3. And so what does that mean for our lattice? So when they're more similar in size, like NaCl, it's going to form a lot tighter and more compact of a lattice because they just fit better together. Whereas with something like R, B, and F, which are quite different in size, it's not going to fit as nicely together. So since NaCl is more compact and fits better together, that's going to have the higher melting point because it's going to take a lot more energy to break that compact structure apart. So our answer for part B is B. And that question, don't worry if it kind of seems a little bit complicated right now. It's a bit more of a challenging question because it requires you to integrate knowledge from like other sections, so like periodic trends. So again, don't worry if that one seemed kind of complicated right now. If you haven't gotten through all of your review, I just wanted to give an example of a question that's maybe a little bit more integrated that you might get. All right, so our next section is on Lewis structures. And so these are a way that we can use to represent compounds with covalent bonds. And so what I'm going to do is just go through the general steps of how to draw Lewis structures, and at the same time I'll kind of use this example of NCO negative to illustrate those steps. So if you have to draw a Lewis structure, the first thing that you're going to want to do is add up your total number of valence electrons. So basically, you're going to want to go through each atom in the compound, see how many electrons it's going to contribute, and then add all of that up. So in this example here, nitrogen is in group 15, so it has 5 valence electrons. Carbon's in group 14, so it has 4 electrons. Oxygen's in group 16, so it has 6 valence electrons. So adding all those up, we have 15. And then if you do have a compound that is charged, then you need to account for that in your number of electrons. So a negative charge adds electrons and a positive charge subtracts electrons. So in this case, we have a charge of -1. So we are going to add 1 electron to our 15. In total, we have 16. And so if you had something that had a +2 charge, for example, then because it's positive, you're going to subtract electrons. And since it's 2, you would subtract 2 electrons from whatever that number is that you calculated. All right, so now you want to kind of start making the framework of your Lewis structure and just connect your atoms with single bonds. Now, sometimes it can be tough to know, which atoms are connected. So I honestly would just say kind of use your best intuition of what you kind of think looks right. As a tip, usually the atom in the middle is going to be your least electronegative atom. Or it's often carbon. So like, for example, that's the case for this compound. So one hint is that carbon's usually in the middle, so you could use that. Also, oxygen and nitrogen are more electronegative than carbon, so you know that those would probably go not in the middle and would probably be more towards the outside. Okay, so once you've done that, you are going to subtract the number of electrons that you kind of have used up now that you've put them in bonds. So every bond is 2 electrons. So here we made 2 bonds. So overall that's 4 electrons. We had 16 total minus those 4 that were in our bonds, leaves us with 12 electrons still to work with. So then our next task would be to take those 12 remaining electrons and distribute them around the atoms in the compound. But we don't want to just do that randomly. Our goal when we're distributing the electrons is to make sure that every atom has what we call a full octet. So what this means is that it has 8 electrons surrounding it. Now there are some exceptions to this. So hydrogen and helium only need to have 2 electrons around them. Boron specifically can have less than 8 electrons. And then elements in row 3 and higher, so by that I mean like row 3, 4, 5, 6, etc., can have more than 8 electrons around them. And so if we look at our example here, we don't have any hydrogen, we don't have any helium, and we don't have any boron. And N, C, and O are all in row 2. So we don't have any exceptions, and everything should have 8 electrons around it. Also, sometimes it's not possible to follow these octet rules without putting some of our electrons into double and triple bonds. So you can also do that in this step if it applies to that situation. Now you'll see with the 3 different options that I've put here, if you actually went through all of the atoms in these options, you'll see that everything does have a full octet. So we're all good there. But then how would we decide which one is actually the correct one? And that's where our 5th check step comes in. And so that's going to help us pick our best or most correct structure. So the first thing that we want to do is check our formal charges and see if they add up to the overall charge of the species. So you can see here I've already calculated the formal charges in blue. And our species has a -1 charge. So overall, all of our formal charges should add up to -1. So you can see that's the case here, that's the case here, and -2 plus 1 also gives us -1, so that's good. So everything is good with this check, But then our second check is, do you have the best Lewis structure? And the best Lewis structure is the one where 1, our formal charges are minimized, and 2, they're consistent with electronegativity. And so I'll go through what each of those means. So an example of a structure where the formal charges are not minimized is this one here. So you can see that it is possible to draw a structure where we just have one charge, which is a -1. But in this case, we kind of overcomplicated things. We've got a -2, we've got a +1. It's just too much. So this structure does not minimize formal charges, so it's not our best structure. And then when we say consistent with electronegativity, what we mean is that we want electronegative atoms to be the ones that have the negative formal charges on them. And so you can see this is an example of something that does not follow that, because nitrogen gets that -1 charge, but it's not the most electronegative atom here. Oxygen is. So this is our best structure because our formal charges are kept very simple, just 1, and it's also that 1 charge is on our most electronegative atom, which is oxygen. So that's all the steps for drawing Lewis structures. Now, keeping in mind that this is a multiple choice test, so you most likely won't be asked to actually draw a structure. It's more likely that you'll get a question that gives you a bunch of options for a Lewis structure and asks you which one is the correct or best one. And so for that, I kind of came up with this little checklist here of like 3 things that you are going to want to check are correct when deciding which is the best Lewis structure. So the first thing is you want to check that the structure has the correct number of valence electrons, so it's consistent with the number that you calculated here. You also want to check that everything has a full octet, or if it is one of the exceptions, that it follows those rules. And then finally, you want to do a check of those formal charges, so seeing if they're minimized and checking if they're consistent with electronegativity. So we already went through the examples with the formal charges, but I just want to give an example here of a structure that is wrong because of its number of valence electrons and its octet. So if we count the number of electrons we have here, we have 2, 4, 6, 8 in the bonds, and then 9, 10, 11, 12, 13, 14 in total. And remember, our number that we needed was 16, so this doesn't have the right number of valence electrons, so it's wrong for that reason. Also, if you look at oxygen, we have 2, 3, 4, 5, 6 electrons around it, so we have an incomplete octet, and so it's also wrong for that reason. Okay, so now we have one of these practice problems here where we're basically given a compound and we're asked to pick the correct Lewis structure. So remember that the 3 things from our checklist that we kind of want to go through are number of valence electrons, checking for octets, and formal charges. So starting with number of valence electrons, we can add that up. So remember, carbon was in group 14, so it has 4 valence electrons. And then hydrogen has 1 valence electron, so if we have 3 hydrogens like here, that's going to contribute 3. And then oxygen and sulfur are both in group 16, so they both have 6. So if you add that up, overall we have 40 valence electrons. Now for the sake of time, I've already added them up for all of these different options here. So A has 38, B has 40, C has 42, D has 42, and E has 40. And so if you want a reminder of how to add those up, basically how I always do it is that I always count each bond as 2. So I just go through it like 2, 4, 6, 8, 10, 12, 14, 16, 18, etc. And then for the lone pairs, I just add those. So for example, here I ended at 34 once I counted all the bonds. And then with these guys here, I just counted 35, 36, 37, 38. So I did that for all of them. These are the numbers that I got. So already this helps me eliminate A, C, and D. So now when I'm deciding between B and E, I'm going to next try and look at octets. And this will get better the more kind of structures that you look at. So I've seen lots of these types of structures. So immediately something that jumped out to me was this carbon here, because it seems to have a lot going on around it. And then if I look, so I'm just going to circle it here, I actually have 2, 4, 6, 8, 10 electrons around it, which is more than our octet. Remember, carbon is not one of these exceptions here because it's not hydrogen, helium, or boron, and it's only in row 2. So it should always have 8 and no more. So that violates that rule. And so that means that E is our correct answer. So looking at it, we have 40 electrons. That was right. And then that carbon, we have our issue is fixed because we have 2, 4, 6, 8 electrons, which is what we want. And so we didn't even end up having to go through formal charges. But I mean, if you did, this is a neutral compound, so we shouldn't have any formal charges. And again, because I've seen lots of these structures, I can already tell that there would be no formal charges here. But if you had extra time and you wanted to go through it, you would see that everything is 0, so everything's minimized and adds up to our overall formal charge of 0. So we know that E is the correct answer.
In this part of the video, we're going to look at formal charges and how you can assign formal charges to compounds. This can be really useful when it comes time to drawing Lewis structures and determining which Lewis structure best represents the actual molecule. A few things just in terms of rules. The formal charge on each atom in a molecule must equal the overall charge in the molecule. We will look at a few examples of where this actually applies. And the negative charge should be associated with the more electronegative atom. We know from periodic trends that our electronegativity increases from left to right and down to up in the periodic table. And the negative charge should be associated with the more electronegative atom because it more wants the electrons. I've also included the general formula for how to calculate formal charges. Now, that being said, I will also show another method that I would consider a shortcut to calculating formal charge associated with any atom. So really understanding how formal charges work, I think, is best illustrated through a few examples. So I've prepared a few examples to show using the equation that I have listed here, as well as the shortcut method. In terms of using this equation, we're going to first calculate the charge associated with the two oxygens that I've labeled with an orange, which contribute to these two. So we know that oxygen, for instance, has a total of 6 valence electrons, meaning the formal charge is going to equal the number of valence electrons, which is 6, minus the non-bonding electrons, which really this means just lone pairs. And these contribute to these here. So we have 4 lone pairs minus 1/2 are bonding electrons, which each bond makes up 2 electrons. So if we have 2 bonds, that means 4 electrons total, meaning then the formal charge associated with our oxygens are 0. That takes into account this one and this one. In terms of our oxygens labeled blue, we already see that there is just based on this picture, negative charges associated with these. However, if we weren't actually given this, we could calculate it based on the same approach using the equation. Formal charge is equal to, it's again 6 because oxygen has 6 valence electrons, minus the number of non-bonding electrons, which you see there is 1, 2, 3, 4, 5, 6, as well as then minus half bonding electrons. We see that atom is connected to sulfur through one bond, which means this contributes 2 electrons, meaning then the formal charge of our blue oxygens is then -1. In terms of sulfur, when we look on the periodic table, it also has 6 valence electrons, just like oxygen. So we know that the formal charge then, again, amount of valence electrons minus the amount of lone pairs it has, because sulfur does not have any lone pairs in it, has it's just filled with bonds. There's 0 lone pairs. And then we go to -1/2 our bonding electrons. We have 1, 2, 3, 4, 5, 6 bonds, which means 12 electrons. We then have a formal charge equal to 0 for our sulfur. Now, that's more a mathematical approach to it. We can now look at more the shortcut. This is the way I prefer. It's both time efficient and it's more a visual approach. So those who might not mathematically understand it, this could be perhaps a better alternative. So the first thing to really do is identify the atom as we had done previously, determining, for instance, an oxygen, sulfur, etc. Then we're going to want to treat all bonds. This is our pi and sigma bonds and valence electrons as single entities. And I'll show you what that means in a second. And you're going to subtract this by the number of valence electrons, and whatever that difference then is going to represent your formal charge. That's a mouthful. I think we should describe this via an example. So I've shown the depiction here. However, I will walk through it step by step. So if we were to draw just the Lewis structure of this, including our lone pairs, I'm not going to draw the formal charges right now, but we know then this is the best representation. So using that same approach, let's start at the very top, at this oxygen. We know oxygen has 6 valence electrons. So you want to, when you're calculating these formal charges, you want to actually start counting one less than the number of valence electrons. So for instance, oxygen, we're going to start crossing off our lone pairs and our sigma and pi bonds starting at 5. So I'll take this one slowly just to show you. So oxygen is 6, 5, 4, 3, 2, 1, 0. That means this oxygen, its formal charge is equal to 0, much like what we see here. In terms of the other oxygen, we can apply the same thing. It's 6, so we go 5, 4, 3, 2, 1, 0. Its formal charge is thus 0 as well. Now, we then look at the other atoms. We know that we can look at, I'll change color just to make it easier seen. We know this oxygen here is also 6, so we're going to apply the same rules starting at counting from 5, 5, 4, 3, 2, 1, 0, -1. So we know this charge, formal charge, is -1, like we see here. Applying the same to our other oxygen, 5, 4, 3, 2, 1, 0, -1. And last but not least, sulfur, if we apply the same, we know it also has a valence electron count of 6, 5, 4, 3, 2, 1, 0. It has a formal charge of 0. Alrighty, this is a good type of exam problem. It's asking uh, the formal charge of each of the atoms in the compound, and it's telling us that all hydrogens and lone pairs are shown. So you can approach this however you would like. If you would like to approach it using the equation or the shortcut I've shown you, I will approach it from the shortcut method. However, feel free to use the other method if you prefer that. So how I'd approach this situation in question is I see it's telling me that all hydrogens in lone pairs are shown, which means then that we don't have to draw in any more hydrogens that are might not be implied or any lone pairs that we would think might need to be shown. They're all shown. So off the start, we have options A through E. I'm going to start on the left here with this carbon. And so with this, we know carbon has 4 valence electrons, meaning if we apply the shortcut, it should be 3, 2, 1, meaning the formal charge of carbon is +1. From here, we can then rule out 2 options already. We know that carbon doesn't have a -1 charge, and we know it doesn't have a neutral charge. So it's either going to be A, C, or E. Now, looking at the next one, if we do oxygen, we know oxygen has 6 valence electrons. So 5, 4, 3, 2, 1, 0. Its formal charge is 0. We can look at our options. We see that both of these still have oxygen as a formal charge 0. So we are going to have to look at our nitrogen for its formal charge. We know that nitrogen has 5 valence electrons, meaning we start counting from 4. 4, 3, 2, 1, 0. Meaning nitrogen has a formal charge equal to 0. Meaning it can't be A, and it can't be C, meaning our best answer here is E. The next topic we're going to look at is resonance structures. These definitely take a lot of practice, and I would say off the start, it is helpful to use arrow pushing. And this just allows you to kind of illustrate where the movement of electrons will go. I find it personally, as a visual learner, helps a lot with being able to see how the movement of electrons causes resonance structures, because in resonance structures, it's not actually the atoms that are moving, it's just either the lone pairs and or the location of the pi bond. And as we've talked about in other topics such as Lewis, atoms that obey the octet rule must also obey the octet rule when doing resonance structures. And also, just as kind of a lookout off the beginning, when you're trying to find which kind of compounds do have resonance structures, you want to see if the compound, for instance, does have a double bond, or in other words, a pi bond, we can call that. So on the right here, I do show a series of resonance structures. So we can see that the movement of the lone pair of electrons can go into the pi orbital. However, in terms of that, if we input 2 electrons, that means that we also then need to output 2 electrons, meaning we can either have an output of 2 electrons here, or we could also have an output of two electrons there, which would give rise to then two different resonance structures. So on the right, I've shown the movement of these electrons giving rise to this resonance structure. Of course, we can also then have movement of electrons here, causing alternative resonance structures, which I've just labeled with, etc. Now, resonance structures, I think, are best identified with practice. So when we look at this question, it says how many of them have resonance structures? So off the start, we know that resonance structures, the approach that I would take is we know that it's the movement of electrons, and we know it depends on delocalization, and that's just really another word of movement of electrons, and also involves pi bonds. So with that criteria, if we were to look at compound 3, for instance, it does not contain any pi bonds, meaning it can no longer, or it doesn't have a resonance structure, meaning right away we know that E cannot be an answer. Okay, so looking at the first compound, we see that it does contain pi bonds, and that is one criteria required for resonance structures. So if we were to treat these pi bonds as a pair of as a lone pair, we actually can have delocalization about the pi bond, causing a resonance structure as follows, which would give rise to a resonance structure as such. And now, one thing I meant to mention in the previous video was that overall this compound is neutral, meaning it should have all the charges in the molecule combine to be, or its resonance structure should have all the charges sum up to what the compound is initially. So in this case, we see our starting compound is neutral, and a resonance structure of that has both a cation and an anion, meaning that it also remains neutral. So we know that at least one of them so far does have a resonance structure, which rules out option A. In terms of our second compound, we see that we have an anionic compound because we have a carbon with a negative charge. This lone pair can be delocalized because of the adjacent pi bond illustrated here, meaning we could have delocalization of our electrons causing the following resonance structure. And again, we can assign then a formal charge to our oxygen, which overall still results in a negatively charged compound. And as a recap, we could assign that formal charge by either using the formal charge equation or that shortcut I showed, where we take the number of valence electrons and start counting backwards, treating our lone pairs and our bonds as one individual. So as a recap, I can show this here. We know that oxygen has 6 valence electrons, meaning we'll start counting from 5. 5, 4, 3, 2, 1, 0, -1. Hence our formal charge is equal to -1. So we know that then we have 2 that have resonance structures, meaning B is not an option. And we already had determined that our third compound does not have resonance because it cannot have delocalization or movement of electrons. So we either then are left with options C and D. And as for our last compound here, we see that we have an anionic species where we could also have delocalization of our electrons, meaning that our fourth compound does in fact have a resonance structure as follows. And again, we can then assign our formal charge if you would like for extra practice. And we can see really what resonance structure comes down to is just the delocalization of electron density. We see that we have a negatively charged oxygen species on the right side, and then a resonance structure of that causes the delocalization of that charge to then be associated with a new oxygen species as follows. So we can confirm that this compound then does also have a resonance structure, meaning C cannot be an answer, and our best representation would be option D.
We're going to chat about Vesper theory. So Vesper stands for valence shell electron pair repulsion theory. Vesper allows us to predict and explain the shapes and geometry of molecules and kind of how they're arranged in a 3D space. The idea that like atoms are surrounded by clouds of negatively charged electrons, and these electron clouds repel each other. So because of this, the molecule will assume a geometry to make sure all atoms are as far away from each other as possible. I'm going to kind of direct your attention now over to the table here on the right. It's kind of just a table I constructed to kind of summarize some of the ideas of Vesper theory. And yeah, it discusses the geometry, the shape, the notation, relates it back to the hybridization, and then an image just to show kind of what it looks like to visualize. This is my note. I may recommend that you memorize a table like this when trying to do Vesper. It kind of, especially in a time crunch on an exam, it might be really helpful to have something like that just to reflect back onto, especially when you're trying to jog your memory. Next we'll discuss the notation that's used. So notation is AXMEN. A standing for the central atom, X standing for the bonding atom, M standing for the total number of atoms bonded to the central atom, E standing for the lone pair, and N standing for the total number of lone pairs bonded to the central atom. This kind of goes hand in hand with steric number, which is the sum of the total number of atoms bonded to the central atom, the total number of lone pairs bonded to the central atom. So next we're going to go through each of the groups, geometry groups for Vesper. First is linear. We can see that there is the steric number of two bonded groups and an angle of 180 degrees between. Next, we'll look at trigonal planar. For the geometry, you can see also that the steric number is three bonded groups, angle of 120 degrees between the bonded groups. Yeah. Tetrahedral is below, steric number of four bonded groups. You can see the 109 degrees between the bonded groups, as well as you can also see what it looks like when it is lone pairs and not bonded groups, especially how it's reflected in the notation. Important note I want to make while we have these two side by side is that lone pairs have more repulsion than bonded atoms. So this means that the bond angle decreases as the number of groups increases. So you can see in trigonal planar, there's three groups, angles 120 degrees, whereas if we add a group down in tetrahedral, the angle is decreased to 109 degrees. So, next, we'll look at the geometry of trigonal bipyramidal, steric number five bonded groups. And now a point I want to make about this, again, I'm just going to reiterate that lone pairs have more repulsion than bonded atoms. So this means that they fill the equatorial axis first for more space compared to the axial axis. So you can see in the images that is 120 degrees between the bonded groups in the equatorial axis, and it is only 90 degrees between the bonded groups in the axial axis. So the lone pairs are going to go on the axial axis to kind of have more space away from each other. Below is octahedral, steric number 6, 6 bonded groups. The angle between all the groups is 90, it is equal. And again, just keeping in mind the lone pair repulsion. Lone pairs populate the furthest away from the other lone pair first. So really clear in AX4E2 that the lone pairs are as far as they can be away from each other because their repulsion is greater. Now, we're going to do some practice, but I just kind of want to make or go through some tips and things to remember, especially when you're doing practice. So first, that Vesper, always try to draw your structure with idealized angles. So this means, for example, in trigonal planar, we saw the angle being 120 degrees. Draw it with that 120-degree angle between the groups when you draw it. Shows the structure better, and yeah. Also, just reiterating that the repulsion between lone pair is greater than lone pair, which is greater than bond pair. We discussed that. So also that this is really important. Vesper does not give any information about bond length and the presence of multiple bonds. Compared to other drawing methods, such as Lewis structures, where you do see double bonds and triple bonds, Vesper does not depict that. So it may be helpful, and I'll show it when we do an example, to draw the Lewis structure first so that you can see if there is double or triple bonds present that affect the geometry of the structure. I'll kind of show that. And so when drawing, I kind of had an error in my typing here. Basically, dashed are bonds going into the page, wedges are bonds going out of the page, solid lines are bonds going into the page. And so this is just used to demonstrate the geometry and shape of the structure. Vesper uses this to show that. So let's do some practice. I'm going to kind of zoom in to make it easier to draw. So we're going to start with our central atom, which is N. Now, I'm going to kind of draw it with Lewis just first, just so you can see like a variation of Lewis. I'm not drawing the lone pairs on the oxygens, but anyway. So you can kind of see how that double bond is there, but when we draw it in Vesper, that double bond does not get shown, as well as the brackets showing the negative charge are not drawn as well. Vesper only shows geometry. It does not show, for example, the negative charge that on the oxygen. Just to make that note, just to remember when you're drawing. So I like to draw my structures first, and then I like to relate it back to the notation. So my notation, I'm going to put it over here, AX3. Now, 1, 2, 3, 3 groups. So 3 groups is trigonal planar. Now, for this one, the geometry and the shape are both trigonal planar. Okay, now let's move down to sulfur dioxide. So again, I'm going to kind of draw it in Lewis just so we can see how there is a double bond, but it is not depicted in Vesper, but to know it's there because it does affect the geometry. So we'll draw this as our kind of Lewis. And then in Vesper, it kind of looks a little bit different. You're just going to draw it like this. Show the lone pair. So relate it back to the notation now. AX2E. E just being for that lone pair, remember. Now, there is 1, 2, 3 groups, but that lone pair makes it so it's not trigonal planar for the shape, but instead it is bent, even though the geometry is trigonal planar. Trigonal planar. And shape is bent. Perfect. So next we'll draw xenon tetrafluoride. See. Now, I'm just going to draw it as Vesper, but pair. Now, we'll do our notation. We'll relate it back. AX4, E for those 2 lone pairs, E2. Now we count 1, 2, 3, 4, 5, 6 groups, so we know we're dealing with octahedral. But those two lone pairs also make note, they're farther away from each other. We know that it is square planar. Perfect. So those are just for an example, a couple practice problems. I might recommend going back and looking at all the examples that I put under the structures. You can work with those for an example as well. And just a reminder, if you have any questions about Vesper theory, put your comments under the video. I'll do my best, or like someone will respond, kind of answering some questions. But yeah, that's it.
The next section we are going to cover is intermolecular forces. So firstly, it's important to know what an intermolecular force is. It's a non-covalent interaction between molecules and is what holds molecules together. So there are three types of intermolecular forces that we are going to cover: dispersion, which are sometimes called London forces, dipole-dipole interactions, and hydrogen bonding. And then I will also touch on ionic interactions. So the weakest intermolecular force are dispersion forces. This force is present in all compounds, but is the only force that is present in a non-polar compound. So a dispersion force is caused by a momentary change in electron density. So at any given time, the electron density, even within nonpolar molecules, such as the ones shown here, may not be perfectly symmetrical, which can cause a temporary dipole. Now this dipole can then act on a neighboring atom, inducing a dipole in it as well, and then the partial charges can align and attract. Now surface area is a key factor here, as increasing the surface area will allow for more space for the interaction, which will also then increase the strength of this intermolecular force. The next intermolecular force is dipole-dipole interactions. Now this force is only present where there are permanent dipoles within the molecule. So in other words, the molecules involved in this interactions must both be polar. In this force, again, the partial positive charge and partial negative charge line up between these polar compounds and are attracted. In this example, we can see that both of these molecules are polar, as the electron density, or pull of electrons, is not equal within the atom. Then the partial charges line up between the molecules. The last intermolecular force is hydrogen bonding, which is when a hydrogen atom is covalently bonded to a lone pair of electrons on a highly electronegative atom, typically fluorine, oxygen, or nitrogen, of a different molecule. Now remember that these are intermolecular forces, so these are between two different molecules. This is not a force that is holding one molecule together. So it is not the attraction or bond between this hydrogen and this oxygen, rather the attraction between the hydrogen and an oxygen of two separate compounds. Now this is very common with water, where the hydrogen of one water molecule bonds to the oxygen atom of the other water molecule. And then finally, I just wanted to touch on ionic forces, which are electrostatic forces between permanently charged ions. Now these are much stronger than any of the other types of forces covered here. One key takeaway from this is that increasing the strength of the intermolecular force within a compound will increase the boiling and melting temperatures. This intuitively makes sense, as the stronger attraction between the molecules, the harder it will be to disrupt or break and change state via melting or boiling. So here's just a practice problem for the intermolecular forces topic. If you want to go ahead and pause the video and work through the problem before I share the answer and how I would approach the problem, you can do that now. So first, again, I would go through the question and pick out some of the key words or key ideas. So which of the following should have the lowest boiling point? This is a really great application question, because not only do you have to understand the intermolecular forces and where they would be present in what types of compounds, we also have to understand the application towards boiling point and melting point. So if we think back to the last slide, we know that the weakest of the three intermolecular forces is dispersion forces, and these are present in all molecules, but they are the only force present in a non-polar compound. Then dipole-dipole interactions are stronger and are present between two polar compounds, but hydrogen bonding is the strongest intermolecular force and is present between polar compounds where hydrogen can covalently bond to an electronegative atom. So based off of this, we can deduce that any molecules that have hydrogen bonding will have the highest boiling point, and compounds that only have dispersion forces will have the lowest boiling point. So from here, I would go through our 4 options and figure out the polarity of them and what types of intermolecular forces would be present in each. So for option A, we know that this is a non-polar molecule because silicon has 4 valence electrons and 4 hydrogen substituents, meaning that there is going to be an equal pull in all directions and no dipole moment, no permanent dipole moment, meaning that dispersion forces are the only forces present in this compound. For option B, we know that this is a polar molecule because phosphorus has 5 valence electrons, but only 3 hydrogen substituents, meaning there's going to be a lone pair of electrons, causing a dipole moment. This means that there are going to be dipole-dipole interactions present. There won't be hydrogen bonding because phosphorus is not electronegative enough. In option C, again, we know that this is a polar molecule because the chlorine is much more electronegative than hydrogen, meaning that it will pull the electron density towards itself. And again, hydrogen bonding will not be present, but dipole-dipole interactions will be. And finally, we know that water is a very polar molecule and contains hydrogen bonding because the oxygen atom is so electronegative, it will covalently bond to the hydrogen atom of another molecule. So based off of this, we know that the correct answer is going to be answer A because it is the only non-polar molecule present in the list and only contains dispersion forces, which are the weakest forces.
I'm Maddie. And I'm Nicole. And we're part of the first year Chem academic mentors. And we're both in 4th year doing an honor specialization in chemistry. So this video is going to touch on valence bond theory and MO theory. First, we can start with valence bond theory. So basically, valence bond theory is based on the idea of hybridization of orbitals. It demonstrates how atoms bond together to form molecules and focuses on the overlap of atomic orbitals of different atoms. And atomic orbitals are the regions of electron density, which is where an electron is most likely to be found. It's primarily based on this idea of hybridization of orbitals, which happens when 2 different kinds of orbitals overlap and mix together and result in hybridized orbitals. The type of hybridization depends on how many orbitals mix together and the coordination number of each atom. It also explains why molecules adopt certain shapes. Underneath here, you can see some examples of different hybridization types. So sp hybridized, sp2, and sp3. On the next slide here, you can see that molecules from the 3rd row and below, which have more electrons, can involve their d orbital in hybridization. So these ones are sp3d and sp3d2 hybridized. This table might be helpful for knowing the hybridization and what kind of orbitals are involved in hybridization. So it shows the coordination number of the atom, the arrangement of the donor atoms, so what shape they'll adopt, the orbitals that are involved in hybridization, and the outcoming hybridized orbital that will result from this. So from the first one, you can see the coordination number of this atom is 2, which means that it'll be a linear shape. The s orbital and the pz orbital are involved in hybridization, and it will result in 2 sp hybridized orbitals. Another important thing to know is that the number of orbitals that go in always have to equal the number of resulting hybrid orbitals. So if we go back to this slide here, you can see this sp3d hybridized orbital involves 1 s orbital, 3 p orbitals, and 1 d orbital that are all overlapping to form hybridized orbitals. This will result in 5 sp3d orbitals that are resulting. So touching a little bit on how a bond is formed based on valence bond theory, each atom has orbitals, which are regions that contain electrons and regions of electron density. And when an orbital of one atom gets close to another orbital, they can overlap. And when they overlap, the electrons from both atoms are shared in that region, which creates a strong attraction, which results in the bond that's formed between the 2 atoms. It's important to know also that the strength of the bond depends on the amount of overlap that there are. So an orbital that is overlapped more strongly with another orbital will create a stronger bond. So more orbital overlap equals a stronger bond. And there are two different kinds of bonds that can be formed. So sigma bonds are caused by the head-on or overlap of atomic orbitals. So like two s orbitals overlapping, or you can see one s and one p orbital, or two p orbitals that are overlapping in the head-on order. They can also form pi bonds, which are caused by the side-by-side overlap of two atomic orbitals. So in this case, you can see there's two p orbitals that are oriented this way, and they're overlapping like this, which is the side-by-side overlap. So it's also important to know single bonds involve one sigma bond. Double bonds, which you can see in the first picture here on the left, involves one sigma bond and one pi bond, and triple bonds involve one sigma bond and two pi bonds. Any covalent bond will always have one sigma bond, and they're the easiest ones to form. And pi bonds are formed using the remaining unhybridized orbitals, and which are typically p orbitals. So I included a practice question here for you guys. If you want, you can pause the video and practice it before I kind of go over the answer and the process on how to solve this. So it's asking, consider the molecule shown below, which orbitals are required to overlap to form the bond indicated by the arrow. So that's this bond here is what we're looking at. Oh. So basically, to start this question, you want to look at the atoms that are involved and closest to the bond and involved in forming the bond. So that would be this carbon atom and then this carbon atom as well. So if we're looking at the first carbon atom, why is it doing that? It looks something like this. So it has the double bond on the top and then the two single bonds as well, which would mean that it has 1, 2, 3 regions, coordination regions or regions of on the molecule that are involved in bonding. So that would give it a coordination number of 3. And then if we're looking at the second carbon atom, which is the one over here, it is like this. It has 3 hydrogen atoms and it's bonded to the other carbon atom, which would mean that it has 1, 2, 3, 4. So a coordination number of 4. The coordination number of 3 would result in an sp2 hybridized orbital, and then the coordination number of 4 would result in sp3. So this carbon atom, this first one here, is sp2 hybridized, and then this other one here is sp3 hybridized, which would mean that the answer for this question would be D, and it requires the overlap of an sp2 orbital and an sp3 orbital.
So the second theory that we're going to be talking about is molecular orbital theory. And so molecular orbitals, or MOs, are formed by the combination of atomic orbitals. And unlike in valence bond theory, which we just talked about, electrons in this are delocalized. So in the first diagram there, you can see that the combination of constructive waves, or in phase, create a bonding MO. And then in the second diagram, you can see that a combination of destructive waves, or out of phase, create an anti-bonding MO. So there are some general rules to follow when you're creating an MO diagram. So it has to follow the Pauli exclusion principle. So each MO can only hold up to 2 electrons and they have to be opposite spin. And the number of MO formed is always equal to the number of atomic orbitals that were put into it. And you have to follow Aufbau principle. So you have to start with filling the lowest energy orbitals and go up from there. And you also have to follow Hund's rule. So degenerate MOs are each given 1 electron before adding another. So in this diagram, the constructive waves of the 1s orbitals form a sigma MO, and the destructive waves of that 1s orbital form a sigma star MO, which you can see there. And the bonding MO is lower in energy than the atomic orbital that it came from because it's now stabilized. And the anti-bonding MO is now higher in energy than the AO that it came from because it's destabilized. And when an MO is formed, no new nodes are created. So in second period molecules, so a little bit further down the periodic table, there's s and p orbitals. So now you can form sigma, sigma star, pi, and pi star MOs. So for pi and pi star orbitals, you have to remember to follow Hund's rule. And the HOMO is the highest occupied molecular orbital, and the LUMO is the lowest unoccupied molecular orbital.
So in this diagram, you're starting with two singular fluorine atoms. So you can see the AOs on the side there. And then when they're mixed, they form the MOs, which is seen up the middle there. And so to find the bond order of a molecular orbital diagram, you have to think about, for a molecule to exist, it has to have more bonding electrons than antibonding, or else it would just fall apart. And so molecules with a greater bond order are more stable. So this is the formula that you'll have to remember for finding the bond order. And your species can either be paramagnetic or diamagnetic. And so if it's paramagnetic, it'll have one or more unpaired electrons. You can see in this diagram that the pi star orbitals each only have one. And for diamagnetic, all the electrons are paired. So in the bottom diagram, you can see that the sigma MO has both the electrons in there. And then I just have a practice question here. So once again, pause if you want to try it. So the question is, which of the following statements are correct about this singlet oxygen MO diagram? So for starting with one, singlet oxygen is paramagnetic. So as we saw in the previous slide, paramagnetic is when one or more electrons are unpaired. So in this diagram, all the electrons are paired, so we know that one is false. For point two, single oxygen violates Hund's rule. And so if we remember, Hund's rule is degenerate MOs each get one electron before doubling them up. So this statement is true because it does violate Hund's rule there. And for the third thing, singlet oxygen has a molecular orbital bond order of 2. So if you count the bonding electrons, there's 2 here, and then 4 there. So you have 8. And then your antibonding ones, which you have left, you have 4. So you have 8 minus 4 divided by 2, which is 2. So that one is also correct. So the answer there is D.
So thanks everyone for watching. If you guys have any questions at all, you can always leave them in the comments and we'll do our best to respond to you guys. And good luck on your exam and the rest of the semester.